Okay, let's talk about how to correct for nearsightedness. So nearsightedness or myopia is the case where your lens can't relax enough, and so things that are really far away appear blurry because your eyeball's too long and your lens can't relax enough, letting those rays go further. Okay, so how do you correct for that? So if we draw a line here, imagine this is the lens configuration, or the complex of lenses. This includes your eyeball lens, cornea, as well as any corrective lens that we're trying to figure out. And then here's the retina, your elongated retina, where you're trying to create that image. So the way a doctor will try and figure out this one is they'll say, okay, the goal is to see something crazy far away. We'll put something out here and we'll say it's at infinity. So its object distance, S, is infinity. Now, they will test without eyeglasses. They'll see, well, what's the furthest thing you can see that's still clear? What's the furthest thing you can see that's still clear? And so they'll test that, and maybe it's out here at this point. You can see that, and it's still clear. You can see closer things too, but you can't see beyond that. Anything beyond that's blurry. So once they figure that out, they say, okay, well, that's where the object, object needs to appear, or that's where the image distance is. So the object's way out here, but you need it to look like it's right there so your eye can focus on it. So that is then where the image needs to be. That would be S prime. And we call that the far point, and I can say of the individual. Okay, I could actually leave that off right now because there is no generic near point or generic far point. Well, there is, but it's infinity. Okay, we're assuming that a healthy eyeball or an eyeball of an average person who doesn't need glasses can see something crazy far away and it's pretty in focus. It may not be easy to tell details, but it's still in focus. Okay, so we have this. This is what object we're trying to see. It's at infinity. This is where we could see it clearly. So we need to figure out the focal length of this lens system such that we can see that. So we just do our 1 over f equals 1 over s plus 1 over s prime. Okay, and now in this case, s is infinity. Okay, so this is 1 over infinity. That goes to 0. And we're left with 1 over f is simply equal to 1 over s prime, which is equal to 1 over the person's far point. All right. Now let's be a little more careful here. Okay, that could give us the number. We just need to measure how far away they can see clearly, and that's the focal length. And 1 over that would be the power of the lens. But is light really going there? When light comes off this object and hits this lens, where does it go? It goes to the retina. It doesn't go back out here. So light's not really coming from it, so that's a negative. And so I'm going to add that as a negative and then the person's far point. Now that means that this focal length of this lens is negative, which is correct. It should be negative or a diverging lens because I need to spread out those rays a little bit more so they can go further before converging. So they can reach all the way back here before converging. So that makes sense. So for someone who is nearsighted, can't see far away, they need diverging lenses for their eyeglasses. Okay, now, this is kind of just a funny story. Every time I go get my checkup, doctors just laugh at me because I have some of the worst nearsightedness that they see, at least on a frequent basis. So I have a far point that is actually closer to my eye than most people's near point. So my far point is about 15 centimeters. That's within the standard person's near point. But I can actually see decently clearly that close, although it kind of hurts. And so I need to wear glasses no matter what I'm looking at. Alright, so if my far point is 15 centimeters or 0.15 meters, then the power, remember that the power of a lens is 1 over the focal length, which in this case is going to be negative because of that minus sign, 1 over the far point, which is 0.15, And so when I divide this out, I have 1 meter divided by 15 centimeters, or 0.15 meters. I end up with a power of 6.6 repeating. Okay, and notice that's unitless because we have meters, I apologize. It's not unitless. This is in inverse meters. I was getting two things mixed up. Apologize. So we have inverse meters there, and this is diopters is the other term for that. But 6.6, if you're not familiar with eyeglass power ratings, that's pretty darn high. Okay, many glasses are in the 2 range, 3 range maybe. And so I have pretty bad eyesight. But that makes me all the more grateful for physics, because physics allows us to be able to correct that eyesight, and now I can function just fine with my corrective lenses. So the main idea, again, just to review, is that for nearsightedness, a person can only see clearly so far away, called the far point, and so they need the image to appear at that far point. And what they want to see is something that truly is physically very far away, or basically infinity. So the object distance is infinity, and we use our regular lens equation to be able to figure out the focal length, or the power as 1 over the focal length.